Hess's Law is section 11.4 in your textbook. Calorimetry is what we've done so far to measure enthalpy, but it's not always possible to use a calorimeter to measure the enthalpy changes in all reactions. There's a few different reasons why we might not be able to use enthalpy changes. The first one is if it's not a dilute aqueous solution and we can't use the specific heat capacity of water. Also, if two products are created simultaneously, we couldn't use it. If the reaction is too small or too powerful to be able to be measured in a calorimeter, or if the reaction is too slow so that there would be energy loss within the reaction. In any of these cases, we use Hess's Law. In Hess's Law, what we are assuming is that the enthalpy change of a physical or chemical process depends only on the initial and final conditions. So on the top left over here, this staircase, if you're going from the top to the bottom of the staircase, it does not matter at all if you go this way, up a couple different sets of stairs, or if you go up the conveyor belt all the way to the top. You're starting from the bottom and getting to the top. Doesn't matter where you get there. So what Hess's Law is saying is that the enthalpy is independent of the pathway. It doesn't matter if there's lots of intermediate steps, that the enthalpy change is only going to depend on where you started and where you ended up. So the diagram on the left, if we're going from A to B, it doesn't matter if you get there using delta H1, or if you're going to go this way through C, or if you're going to go down through D and E, the enthalpy is still going to be the change between A and B. We're going to do this in two different ways over the next couple days. What we're going to talk about today is 11.4, which is adding relevant reactions. 11.5 is a variation on Hess's Law when we're using enthalpies of formation, and that's what we'll do next. If we wanted to, we could represent Hess's Law as a formula, which is essentially just saying that the total enthalpy change is going to be an addition of all of the enthalpy changes that are intermediary. Hess's Law is going to be, we're going to use it based on two different rules that we've already discussed. The first one is that if we reverse the chemical reaction, then we change the sign of our delta H from negative to positive or positive to negative. The second one is that if we multiply or divide a coefficient of a chemical equation, that we're going to have to do the exact same thing to the delta H, to our enthalpy change. In the green box down here, it's saying that using Hess's Law is essentially trial and error. You do whatever you want to the equations, flip them, multiply them, divide them to get the equation that you want in the end. The problem that we've been given here has given us no information except for a reaction. So we're not going to be able to use the formulas that we've used already, such as Q equals MC delta T, in order to find out anything about it. The only thing that we can find out about any of the compounds in the reaction is based on our data booklet. So if we flip to page 4 and 5 on our data booklet, we have the standard molar enthalpies of formation of compounds. So I'm going to start by writing the formation reactions with the molar enthalpy of all of the compounds here. So here are my three formation reactions, and I wrote them all so that we have 1 mole of each of the products being formed. If you look at your data booklet, you will find that for the first reaction, we have the change in enthalpy for formation in standard conditions is equal to negative 634.9 kilojoules. And it is per mole, but since I wrote the reactions for only 1 mole, we can say that it's also kilojoules. For water, liquid water, it's negative 285.8 kilojoules. These three reactions can now be used to make my final reaction and calculate my enthalpy change of the reaction that is underlined in blue above. So in Hess's Law, I can manipulate these reactions in any way. I can flip them, I can multiply them, or I can divide as long as I do the same thing to the delta H value. So what I'm going to do is I'm going to look for each part of the reaction that I'm looking for, the one underlined in blue, and see where I can find it in the reactions that I have. So the first thing I have up here is I have calcium oxide. I'm going to see where calcium oxide is in the reactions that I have in black below. You can see that in the first one we have calcium oxide as a product, and we want calcium oxide to be as a reactant. So I am going to take the first one and I am going to flip this reaction in order to make sure that calcium oxide is in the reactant where I would like it to be. So I've just flipped my reaction, and because I'm flipping it, what I have to do is I also have to change the sign on my delta H. So this has gone from an exothermic reaction as I had it written at the top, and because I flipped it, it's now an endothermic reaction. I can now do the exact same thing for water, because you can see that water is a reactant, what I'm looking for, and it's a product in the reaction that I have, so I'm going to flip this second reaction as well. And because I've exactly flipped it, I have to do the exact same thing to my delta H and flip it into an endothermic reaction as well. The last thing that we're looking for is calcium hydroxide, and you can see that calcium hydroxide is a product in both situations, so we can keep the exact reaction that we already have. Now what you can see is you can see that the calcium right here and the calcium right here that we don't want in our final reaction actually cancel each other out. And the other thing that you'll see is that we have a hydrogen on the right here and a hydrogen on the left here, which cancel out. And on the right-hand side, we have one oxygen. Sorry, on the left-hand side. And on the right-hand side, we have two half oxygens. So those will cancel out as well. Now all I'm left with is exactly the reaction I was looking for. So what I did there was I added up the reactions. So I'm going to do the exact same thing with the changes in enthalpy for each reaction. And I will get that my final change in enthalpy in standard conditions is going to be negative 64.5 kilojoules. And that means that for 1 mole of my calcium hydroxide, it is an exothermic reaction, and it is going to release 64.5 kilojoules. In this example, you're not given the reaction that you're looking for, but what you are given is that you're looking for the formation of SO3. So the first thing we have to do is write down the formation of SO3. So the reaction that I've written here is the formation reaction for 8 moles of SO3. You could divide the entire thing by 8 and have fractions, but it makes it a little bit more confusing. So what I need to make sure that I do at the very end is divide my final answer by 8 so that it's representing only 1 mole of SO3 being created. So first what I'm going to do is I'm going to choose something in my blue reaction here that I see above. I'm going to choose S8, and the reason I'm going to choose S8 is because it only appears in one of the reactions above. Oxygen appears in both, so it's a bit more difficult to start with oxygen. So here I have my reaction, which includes S8, but the problem that I have now is that on the right-hand side in the product, I have SO2, and I don't want to have SO2. So what I need to do is I need to find something that will cancel out my SO2. The other thing, in the end of our blue reaction as a product, I have SO3. So that means I'm also going to have to take my SO3 and put it into the product. So the second reaction that I have up here, if I flip it, I could facilitate both of those problems. I could put my SO2 into the reactant, and I could put my SO3 into the product. So I'm going to flip it. So here in red, you can see my second reaction has been flipped. And because it's been flipped, I had to flip the sign of delta H as well. So it's now representing an exothermic reaction. So the problem that we have right now is we can't cancel all of the SO2s. I have 8 SO2s on the right-hand side and 2 SO2s on the left-hand side. Also, what I'm looking for in my blue reaction at the top is 8 SO3s, but right now I'm only making 2 SO3s. So what I need to do now is I need to take this entire reaction and I'm going to have to multiply it by 4. Because if I take it and I multiply it by 4, what will happen is I will have the 8 SO3s that I want to have, and I will also be able to cancel out the 8 SO2s that I want to get rid of. When I multiply this reaction by 4, I also have to make sure that I'm multiplying the enthalpy by 4. Because if I have negative 198.4 kilojoules for 2 moles of SO3 being created, I'm going to have 4 times that for 8 moles of SO3 being created. So what I've done now is I've rewritten both of my equations. So you can see that the one up here in green has been rewritten right here, the exact same, with the exact same enthalpy change. But the second one, my red reaction, I've rewritten it multiplied by 4. So I have 8 SO2s plus 4 O2s goes to 8 SO3s, and I've also changed my enthalpy. Now I'm going to cancel out. As you can see on the top equation here, I have 8 SO2s that will cancel out the 8 SO2s in my bottom equation. Now I'm being left with exactly what I'm looking for. I have 8 S8 plus 12 O2s goes to 8 SO3s. So now all I'm going to do is I'm going to add everything up. So here we have that for the production of 8 SO3s, we are going to release 3,528 kilojoules. But if you remember, the question said that we wanted the molar enthalpy, or for 1 mole, which means we have to take this and we have to divide it by 8, which will leave us with 1/8 S8 plus 3/2 O2 goes to 1 SO3. And we need to do the exact same thing with our delta H value, which will give us a final delta H of negative 441 kilojoules. And that's what will be released for the creation of 1 SO3. Last thing, thermal stability is the ability to resist decomposition. And decomposition, remember, is the opposite of formation. And that's the ability to resist it when it's being heated. If we think about the most stable compound, and we think about that in an endothermic reaction, it is going to take energy in, and in an exothermic reaction, energy is going to be released. But when we think about decomposition, the more endothermic something is, the more endothermic that the reaction is, that means it's going to take more energy to decompose it. So if your reaction is really, really endothermic, it's going to take a lot of energy to decompose it, and we can say that it is more stable. Same thing for decomposition, the more exothermic, the less stable it is going to be. So for decomposition, you always want to remember that the more endothermic it is, the more energy it is going to take to break it down, and therefore the more stable it will be. Here's an extra practice question. It's a more challenging problem if you would like to give it a try. Here's stuff to work away on to practice what we just talked about.